Hello everyone. So in this video we will discuss about the properties of discrete time Fourier transform. So we have already seen the properties for the continuous time Fourier transform, and the form of the properties of discrete time Fourier transform is quite similar to that we have discussed in the continuous time case, but there are some quite significant differences which arises due to the discrete nature of discrete time functions, and we will see as we move on into this lecture. So we will start with our first property. So first property is your periodicity. So it is quite evident that a discrete time Fourier transform is always periodic with period 2 pi. So it will be always periodic with period which is equivalent to 2 pi. So how we can understand it? So we have seen that x of e raised to the power j omega is the Fourier transform of signal xn. So they form a Fourier transform pair. So we have a Fourier transform pair xn who is having a Fourier transform of x e raised to the power j omega. So what we are saying that if we take e raised to the power j omega plus 2 pi, we will get the same Fourier transform, that is x e raised to the power j omega. So this is the property of periodicity of a Fourier transform, especially discrete time Fourier transform. So this property was not there in the continuous time case. So next we will discuss about the linearity property. So the property is linearity. So suppose we have x1n as a signal whose Fourier transform is given as x of e raised to the power j omega. So it is x1 e raised to the power j omega, and suppose we have a different signal x2n which is having a Fourier transform of x2 e raised to the power j omega. So what this property states that if we'll take the Fourier transform of a of x1n plus b of x2n, that will be equivalent to small a multiplied with x1 e raised to the power j omega plus small b multiplied with x2 e raised to the power j omega. So Fourier transform follows the property of additive and homogeneity. That's why it is having a linearity property, and that can be evident that we have multiplied the signal with some scalar a and b, and then we have added both signals. So the same operation happens at the frequency domain as well. The individual Fourier transform is multiplied with the scalars, and we get a overall summation of these two Fourier transform. So this is the basic property of linearity. Now we'll discuss the next property, which is time shifting. So time shifting, as we have already discussed, what it means that we are either advancing or delaying the signal in the time domain. So suppose we have a Fourier transform pair xn and having a Fourier transform of x e raised to the power j omega. So this property states that x of n minus n naught will be having a Fourier transform of e raised to the power minus j omega n naught x e raised to the power j omega. So as you can see that here we are shifting the signal in the time domain, and it is analogous to multiplying our Fourier transform with a factor e raised to the power j omega n naught. Again, it is similar to that we have discussed in the continuous time case. So here again the magnitude is not changing, only the phase value is changing. And similarly we can have an equivalent shifting in the frequency domain as well. So suppose what will happen if we'll do shifting in frequency domain. So this statement is equivalent to having a factor e x of e j omega minus omega naught. So here what we have done, we have shifted the signal in the frequency domain. So that is equivalent to having a factor multiplied with e raised to the power j omega naught n multiplied with x of n. So you have to be careful with the sign. So here if we did n minus n naught, we'll get a factor of e raised to the power minus j omega n naught, and here if we did the shifting in frequency domain, we get a factor which is represented as e raised to the power j omega not n. So there is a significant change in sign. And also so this is domain, so I'll just replace it with, so these are the property of time shifting and frequency shifting, and again they are like quite similar to that of its continuous time counterpart. So next we will see the property of conjugation and conjugate symmetry. So next property is our conjugation and conjugate symmetry. So what this property state that, suppose you have a Fourier transform pair xn having a Fourier transform which is equivalent to x e raised to the power j omega, and we take the conjugate of xn in the time domain, it will be equivalent to taking conjugate of the Fourier transform function which is a change in the sign, that is e raised to the power minus j omega. And again if xn is real, so what will happen, we'll get x e raised to the power j omega which will be equal to x conjugate e raised to the power minus j omega. So this property holds only when xn is real, and this is basically represented as conjugate symmetry. So this is your conjugate symmetry. So next, so this is also like quite similar to that with the continuous time counterpart. Next we will discuss about a different property which is different in case of discrete and continuous time. So in continuous time case we have studied about differentiation and integration property, but here that is changed to differencing and accumulation. So they are the analogous to differential and integral, which is differencing and accumulation. So the property state that it is differencing and accumulation. So what this property state that, suppose we have a signal xn and we take a difference it with x of n minus 1. So this is called the difference, first difference basically. So it will have a Fourier transform of 1 e raised to the power minus j omega x of e raised to the power j omega, and you can directly derive this from the time shifting property, because the Fourier transform of this will be x of e raised to the power j omega, and for this it will be e raised to the power minus j omega x of e raised to the power j omega, and when we solve we will get this part. Now for accumulation, how can we derive it? So suppose we said there is a signal yn which is equal to accumulation of xm over the interval minus infinity to infinity. So we have done a summation of xm with a range minus infinity to infinity. Suppose we have take yn minus of yn minus 1. So what will be this factor? It will be xn. So you can do directly get this result from this expression. And now if we'll take the Fourier transform of particular signal, so what we'll get? We'll get y e raised to the power j omega minus e raised to the power minus j omega. This is because of the shifting property, time shifting property, y e raised to the power j omega, and the right hand side will be x of e raised to the power j omega. So this step is basically taking Fourier transform of this expression. So when we rearrange it, what we'll get? We'll get y e raised to the power j omega, which is equals to x e raised to the power j omega divided by 1 minus e raised to the power minus j omega. So as we have taken yn as the accumulation of xn, so its Fourier transform is x e raised to the power j omega divided by 1 minus e raised to the power minus j omega. But this is not the correct answer, because as we have seen that in the integration case there are some constant added to it that is representing the DC or average part. So here also the complete representation of this accumulation property can be given as, suppose xm is having a Fourier transform of 1 minus e raised to the power minus j omega x e raised to the power j omega, that we have seen that we have got this result. Apart from that, there will be some added average or DC values to it. So they are some constant values. and this is quite similar to that of the integration property which we have studied in the continuous time case. So derivation is not important here. You have to just remember this formula in order to derive the examples. So here we'll just take one example to understand this property. Suppose we want to take a signal xn is equals to un and we want to get its Fourier transform, though we can directly get it from the formula of Fourier transform for discrete time case, but here what we'll do, we'll make use of differencing and accumulation property, especially the accumulation property, and get the Fourier transform of it. So how we'll solve it? Suppose we have xn as un, so we will take a signal gn which is represented as del n, and we all know that the Fourier transform of gn will be g e raised to the power j omega, which is equals to 1. And now gn and xn has a very similar relationship, we have already seen earlier also. So xn will be represented as integration of basically summation, because it's a discrete time case. So we'll take minus infinity to infinity g of m. So if we will take the running sum of delta function, what we'll get? We'll get the unit step function. So this expression shows the running sum. So now we'll take the Fourier transform by using this formula which we have seen in the previous property. So that directly says that the Fourier transform of x e raised to the power j omega will be 1 minus e raised to the power minus j omega multiplied with capital G e raised to the power j omega, which is the Fourier transform of g n, that is added up with pi j of g of e raised to the power j 0 summation k is equals to minus infinity to infinity del of omega minus 2 pi k. Now we'll replace the value of g e raised to the power j omega as 1 here, and that will be equal to 1 upon 1 minus e raised to the power minus j omega plus pi. This value will be also 1, and it will be equal to summation k is equals to minus infinity to infinity del of omega minus 2 pi k. So this is the Fourier transform of your unit step function, and this is very useful, so it can be widely used further in this lecture. So now we have seen this basic property. Now we'll move on to another different property which is quite significant in case of discrete time case. So here we'll discuss about the time expansion. So we have seen the scaling property in case of continuous time case, but here there is some difference because of the discrete nature of these kind of signal, we have to define the scaling in a different manner. So here we define xkn, which will be equal to x of n by k. So this express the expansion of the signal, and it will be if and only if n is multiple of k, because we know that the discrete time function takes values only at discrete value of n. So this value will be x n by k only when n is multiple of k, and for all other values it will be 0. So if n is not multiple of k. So in this way the expansion is defined. So how we can get the Fourier transform of it? So we'll just do a quick derivation of it. So suppose we want to get the Fourier transform of this, so what will be the representation? It will be x of k e raised to the power j omega, and that will be equal to summation n is equals to minus infinity to infinity x of k, which is the showing the expansion with a factor of k, and that will be n e raised to the power minus j omega. So this is from the formula of Fourier transform. So now what we will do, we will represent it as summation x of k r k e raised to the power minus j omega r k, and r will varying from minus infinity to infinity. This is from the fact that it will only have some value when n is multiple of k. So we have replaced n with r k, which is showing that it is multiple of r. So that's why we shown it as x of k multiply with a factor of r k, and if we represent x of rk as of x of r, which is indicating the same thing. So what we'll get x of e raised to the power j omega, which will be equal to summation r is equals to minus infinity to infinity x of r e raised to the power minus j k omega into r, which will be equal to x e raised to the power j k omega. So you can see that there is a factor of k here. So what we have get when we do the time expansion, so we suppose we have done some expansion of the factor k, so your Fourier transform of this signal will be shrink by that factor e raised to the power j k omega naught. So the frequency will be increased, so it will be more likely to be shrinked in the frequency domain. So to visualize it, I will just give you one figure from the reference of Oppenheim book. So there is one beautiful picture explaining all this property using the single image. So we will just see what is happening here. So here, as you can see, we have a discrete time signal. So this is your signal, and it is having a Fourier transform of this, which we have seen also derived. It is having some factor of sine omega n1 plus half by sine omega by 2, like that factor, and it's also periodic. Now what we have done, we have added a factor of 2, so there will be zeros will be imparted in between two values. So because of the factor, what will happen when we put a k value of 2, what will be, it will be x n by 2. So it will take only the second samples and all other values will be 0. So now you can see that there is a frequency is having x e raised to the power j 2 omega, and it is felt like it the frequency domain is shrinked, and similarly as the factor increases, there will be more shrinking in the frequency domain. So this signifies the inverse relationship between time and frequency domain. So expansion in one domain relative to shrinking in the other domain, and vice versa. So this is the property of time expansion. So now we'll see the basic property of Parsevals relation. So we'll discuss the Parsevals relation, and it is similar to that we have discussed in the continuous time case, only the form is different. So suppose xn is having a Fourier transform of x e raised to the power j omega. So the factor n varying from minus infinity to plus infinity x of n. So this represents the energy of the signal, which will be equal to 1 over 2 pi integral over 2 pi x e raised to the power j omega mod square du. So we get the energy from this formula from either of the domain. So from time domain, this expression will be giving the energy of the signal, and from frequency domain we can use this signal as per the question given. So suppose if only the frequency domain data is given, you can directly calculate the energy of the signal using this formula. So we'll discuss the last property as convolution property. So the convolution property states that this is very simple, as we have already derived and explained in the continuous time Fourier transform. So we'll just give the statement of it, and we'll see some of the numericals related to all of these properties. So yn will be equal to xn h of n. So yn is a signal which is the convolution of xn and hn. So hn represents the impulse response of a system. So what will be y e raised to the power j omega? So yeah, it's just a multiplication of these two. So x e raised to the power j omega multiplied with h of e raised to the power j omega, and these two represent the Fourier transform of the respective values. So now we'll see some numericals related to these properties. So suppose we have a system in which the impulse response hn is given by alpha n un, where mod alpha is less than 1, and the input to that system is represented by xn, which is represented as beta raised to the power n un, and again mod beta is less than 1, and we are interested to get the Fourier transform of output which is represented as y e raised to the power j omega, and we all know that in order to get y of n, we have to first calculate the convolution of xn with hn. Here we will use the convolution property. So what we will do, in order to get the Fourier transform of the output, we have to calculate the Fourier transform of the input, and we will multiply these two. So this will be the Fourier transform of the impulse response, and we will multiply, and we will get the Fourier transform of the output, and then we will take the inverse Fourier transform of this expression in order to get the yn. So we will do it step by step. So the first step is to calculate the respective Fourier transform. So our hn is given by alpha n un. So its Fourier transform we have already derived, and you can also do it by applying the formula. It will be given by 1 minus alpha e raised to the power minus jn, and similarly xn will be given by beta raised to the power n un. So the Fourier transform of this expression will be 1 by beta e raised to the power minus j omega. Now from the convolution property which we have stated earlier, the y e raised to the power j omega, that is the Fourier transform of the output, is represented by multiplication of these two. So it will be h e raised to the power j omega multiplied with x of e raised to the power j omega, and it is quite evident that this value will be 1 over 1 minus alpha e raised to the power minus j omega multiplied with 1 minus beta e raised to the power minus j omega. Now since this is the form, we can use partial fraction here. So we will use partial fractions to solve this. So we will write the expression of partial fraction as y e raised to the power j omega is equals to 1 over 1 minus alpha e raised to the power minus j omega plus b over 1 minus beta e raised to the power minus j omega. So we will compare these two expressions. So the LHS will be same. So we can calculate the right hand side, and from that we can get the value of a as alpha over alpha minus beta, and the value of b will be equal to minus beta alpha minus beta. So these will be the two values for a and b, and now we will substitute these values in the expression of y e raised to the power j omega. So it will give us y e raised to the power j omega, that will be equal to alpha minus beta multiplied with 1 over 1 minus alpha e raised to the power minus j omega, and the other one will be minus beta over alpha minus beta 1 over 1 minus beta e raised to the power minus j omega. So this is the expression. Now when we take the inverse Fourier transform, so these are the simpler form Fourier transform. We have already seen that the Fourier transform of inverse Fourier transform of this expression is equivalent to this expression. So here we have to just replace these values. So what will be the output? Output will be yn, that is the inverse Fourier transform of this expression, which will be equal to alpha by alpha minus beta alpha raised to the power n un. So this is the inverse Fourier transform of this expression. Similarly, we can write it as minus of beta alpha minus beta, and the inverse Fourier transform of this expression as beta raised to the power n un. So this is our expression of yn. So this is the final form of the expression of the yn. So here we have started with calculating the Fourier transform of the individual signals. So we have calculated the Fourier transform of impulse response and the input signal, then we multiplied them and we get the Fourier transform of the output, and then we calculate the IFT to get the yn. So this makes the calculation very easy. Otherwise we have to calculate this convolution, and that will be a complex calculation. Now here one question arises, that what happens when alpha is equals to beta? So is it so that we will get some values divided by 0? So this is not the case. When alpha is equals to beta, you cannot use this partial fraction form. Then what will happen? Suppose if we will use alpha is equals to beta, so y e raised to the power j omega will become 1 over 1 minus alpha e raised to the power minus j omega, and this beta will be also replaced by alpha. So this, when this 2 multiplies, it will make a square. So when alpha is equals to beta, so when alpha is equals to beta, so what will be y e raised to the power j omega? It will be having a form of 1 over 1 minus alpha e raised to the power minus j omega square. Now here we can use frequency differentiation property, though it's not quite evident that which property to use, but we can see that how we can use frequency differentiation property to solve this problem. Though there are other methods also, but just for the sake of understanding the properties well, we will use the frequency differentiation property. So how we can write y e raised to the power j omega? We can write in a different form like j over alpha e raised to the power j omega d by d omega over 1 over 1 minus alpha e raised to the power minus j omega. This is just the form getting by some analytical interpretation of this expression. So what we'll do, when we take the derivative of this expression and multiply these constant with this, we'll get this expression back. So here you can see, now we'll use the frequency differentiation property. So we'll use frequency differentiation property. So suppose if we have the Fourier transform of alpha raised to the power n un as 1 over 1 minus alpha e raised to the power minus j omega. So if we will multiply n at the time domain, so it will be n alpha raised to the power n un, and its Fourier transform will be j times d over d omega of 1 over 1 minus alpha e raised to the power minus j omega. So now you can see some similarities between this expression and this expression. So we got that j d over d omega of 1 over 1 minus alpha e raised to the power minus j omega n. So now if we'll see that how these two can be interpreted. So as you can see, there is a e raised to the power j omega factor in the frequency. So can you guess like what will be the effect equivalent in the time domain? So yes, it will be a time shifting operation, but it will be a time delay of 1 unit. So how we can interpret it as? So now we want an e raised to power j omega, so we'll just have to delay our signal with one factor. So we'll get n plus 1 e raised to the power, sorry, it will be alpha n plus 1 u of n plus 1. Its Fourier transform will be j over alpha e raised to the power j omega d over d omega of 1 over 1 minus alpha e raised to the power minus j omega. So as you can see that this form is quite equivalent to this form which we are calculating. So now we have our Fourier transform of this yn will be equal to, so the signal yn will be equal to n plus 1 alpha raised to power n u of n plus 1. Here n plus 1 is compensated with this division of alpha, and now also this can be equal to yn, which will be equal to n plus 1 alpha raised to power n un, because if we will put n minus 1, so this factor will make it 0. So effectively the signal is starting from 0, so we can replace un plus 1 from yn. So these are the same equivalent expression. So we'll say that this is the final expression of the output. So this is the case when alpha was equal to beta, otherwise this expression holds good. So now we'll see some solution related to the LTI system. So how these properties can be used in the LTI system. So suppose we have a causal LTI system. So we have a causal LTI system, yn minus 3 over 4 y of n plus 1. So this is n minus 1 plus 1 over 8 y of n minus 2, which is equals to 2x of n. So, and we wish to get the impulse response of this causal LTI system. So we want h of n. So we will first calculate the Fourier transform of this expression. So it will be equal to y e raised to the power j omega minus 3 over 4 e raised to the power minus j omega y of e raised to the power j omega plus 1 over 8. Again the time shifting is of 2 factors, so it will be e raised to power minus j 2 omega y of e raised to the power j omega, which will be equal to 2x of e raised to the power j omega. Now when we'll rearrange, it will be equal to y e raised to the power j omega over x e raised to the power j omega, that will be equivalent to 2 over 1 minus 3 by 4 e raised to the power minus j omega plus 1 by 8 e raised to the power minus j 2 omega. And we know that the ratio of the Fourier transform, the output and input, can be represented as your Fourier transform of your impulse response. So this will be the expression for h e raised to the power j omega, and h e raised to the power j omega we can write in the factorized form as 2 over 1 minus 1 by 2 e raised to the power minus j omega, then it will be multiplied with 1 minus 1 by 4 e raised to the power minus j omega. So this is just the basic factorization using basic mathematics. Now what factor we are getting? We'll now split it into two parts. That will be equal to 4 over 1 minus 1 by 2 e raised to the power minus j omega minus 2 over 1 minus 1 by 4 e raised to the power minus j omega. So it will be this form. So now we'll take the inverse Fourier transform of this expression. So we'll take the IFT. So it will be, so this is the expression for the impulse response of the causal LTI system, and we have rearranged in the form that we can directly get the output as 4 1 by 2 raised to the power n un minus 2 into 1 over 4 un. So we'll solve one final example to understand the properties. So here, suppose we have a causal LTI system represented as yn minus alpha y of n minus 1, which is equals to x of n, and now we wish to again calculate the impulse response of this signal. So we'll first take the Fourier transform. So y e raised to the power j omega minus alpha e raised to the power minus j omega y e raised to the power j omega. The Fourier transform of the input will be x e raised to the power j omega. So we've just taken the Fourier transform of this expression, and this factor arises due to the time shifting at the time domain. Now we again take the ratio of y e raised to the power j omega by x of e raised to the power j omega, and that will be equal to 1 by 1 minus alpha e raised to the power minus j omega. And again we'll take, and this will be the factor for Fourier transform of the impulse response, because it is the ratio of the Fourier transform of the output and the input. And when we take the inverse Fourier transform of this expression, so we'll take the IFT of this expression, we'll get Hn as alpha raised to the power n u of n. So this is the impulse response of this system. So in this lecture we discussed all the properties of discrete time Fourier transform, and we try to solve some of the problem using these properties. Thank you.